Hi. In this presentation, we will briefly look into the main reasons that led to the development of the IEEE 1149 standard, the boundary scan test technology. After watching this presentation, you should be able to answer the three questions in the title. Why boundary scan is an important test technology, what is its application domain, and also how are the test vectors applied to the circuit under test and the test responses captured. There were two main reasons that led to the development of boundary scan in the mid-1980s, and they were related to the challenges faced by two main test technologies, functional testing, which is illustrated in this slide, and in-circuit testing, which we will consider in the next slide. In the case of functional testing, only the edge connectors are used to drive test patterns and to capture the test responses, so there is no physical access to internal printed circuit board nodes. If we want to find out whether there is a short circuit between these two nodes, for example, we must be able to drive opposite logic values to the corresponding output pins, but how can we find out what test values to drive at the input edge connector in order to set up these fault detecting conditions? And how can we propagate the error signal to an observable pin at the output edge connector? Well, in-circuit testing, on the other hand, enables physical access to the internal nodes in the printed circuit board by using very small test needles, as shown here, organized in a mechanical jig known as bed of nails. This became increasingly difficult as the pins in the integrated circuits became closer and closer, and as it became common to mount the devices on both sides of the printed circuit board, not to mention multi-layer boards or even protective coatings that prevented electrical contact. In-circuit testing also has to cope with what is called backdriving, since a test needle may be trying to drive a logic 0 while the output pin it is connected to is driving a 1. Well, boundary scan embeds one small test cell adjacent to every functional pin. These small test cells have two main operating modes. They can work in transparent mode, in which case everything happens as if the test cell was not present. Or they can work in test mode, whereby they will isolate the pin from the core logic and make it possible to drive any given logic value to an output pin. It is also possible to capture the resulting test response at the input pins located on the other side of the printed circuit board interconnect. And notice that backdriving is no longer a problem because the boundary scan cells isolate the output pin from the core logic. Well, as shown in this slide, we can drive the two opposite logic values to the two output pins and then capture the logic values arriving at the corresponding input pins. In this case, we should capture a 0 and a 1 if there is no fault present, or the same logic value, either 1 or 0, whatever is stronger, if the short circuit is present. Moreover, and since the boundary scan cells are interconnected as a long scan chain, we can shift in the test vectors using a serial test data input, or TDI pin, and shift out the test responses using a serial test data out, or TDO pin. Boundary scan became an IEEE standard in 1990 and is now very popular, and actually use it for various other purposes other than detecting shorts and opens, such as in-circuit debugging or FPGA programming. But it is important to keep in mind that it was originally developed to cope with the increasing problem of detecting defective interconnects. As such, there are three keywords that describe the main application domain of Boundary Scan. It was created for structural testing in digital printed circuit boards. And that's all for now. Thanks for your attention.